So this talk will be related to some different papers. I mean, different papers related to teleparallel gravity and black holes. Actually, not only scalarized black holes. And this is paper. The last paper is in collaboration with Christian Pfeiffer and Ludovic. And yeah, let's start. So. This is the order of my presentation. First, I will talk about teleparallel gravity because I will spend quite a lot of time introducing this because it's maybe it's not familiar for the audience today. So some basic mathematical ingredients. I will explain about teleparallel equation of GR, and then I will explain about black hole solutions in teleparallel gravity, both without the scalar field and with a scalar field, which is related to this scalarized black hole solution that we found with Christian and Ludovic. And I will find if I have time, I will have some conclusions at the end. So okay, so let's start with the basics. So I don't know what is it. Okay. So in teleparallel gravity, we don't have the standard Riemannian connection. So for this, let's briefly mention what happens. So in the most general metric affine gravity, one has the metric, the standard metric tensor with 10 components, but also we also have the so-called the affine connection. The most general connection in general has 64 components. This is the most general affine connection that you can construct from geometry. And one can split this connection in several pieces. So the first piece is just the standard one, the so-called Levi-Civita one. By the way, this tilde here represents like the general affine connection. You can split in several pieces. The first piece is related to the standard Levi-Civita tensor connection. Then we have some extra terms that in general relativity they are always zero, or in Riemannian case is always zero. In the Ludovic's talks also was set to zero, and it was in the standard Hordensky gravity. So one has this torsion part, and also one has this non-metricity part. And this tensor here are geometrical quantities that they are related to this affine connection, like the torsion tensor is related to the antisymmetric part of the connection, and non-metricity tensor is related to the covariant derivative of the metric. So in GR, when you put this non-metricity to zero, you have the so-called compatibility condition, and you also assume that you have the connection to be symmetric, so you don't have torsion. So usually this is the case in GR and the majority of the theories in modified gravity and in scalar-tensor theories and so on. But in this presentation, I'm going to focus in a theory which is different. It's not the same connection as Riemannian case. So in this case, we will have some torsion terms, but it's a very particular one. It's not the one that we have curvature and torsion, but it's the one that we only have torsion. This is the so-called teleparallel gravity. Okay, so just to set some notation, so I use these Greek letters to denote space-time indices and Latin letters to denote tangent space. We need this because it's much simpler in teleparallel gravity to work with this notation and to introduce the so-called tetrads. Okay, so we introduce tetrads or Bierfein. It's also possible to formulate the theory without tetrads, but it is simpler to understand in this way. So these tetrads are just linear bases on our space-time manifold, and each point of this space-time, the tetrads give us some basis for vectors on the tangent space. This is the definition of this E that is the tetrad field. Yeah, also one important thing, one remark. Levi-Civita, all the terms that it will contain this circle on top, this will mean that I am talking about the Levi-Civita connection. Okay, this is just the notation. And also, okay, the inverse of the tetrad I will denote by this capital E. Okay, so tetrads satisfy the so-called orthogonality condition. So if you contract them with the inverse with the tetrad, you just get the chronicle delta with the Latin letters and also with the space-time indices. More importantly, one can reproduce the metric with the tetrad. So you have a tetrad E, then you just use this equation here, and when eta is just the Minkowski metric. So you put the tetrad here, you multiply like somehow the square it, something like that. You put it with the Minkowski metric, and then you obtain the metric. This is not like it is not something related to teleparallel gravity. I mean, you can always introduce tetrads in even special relativity, also in general relativity, but in this context, it's much simpler to work with tetrads. Okay. So okay, now let's go to the teleparallel condition. So in the teleparallel gravity that I'm going to talk doesn't have non-metricity. There is another version of teleparallel gravity that it contains non-metricity, but in this version we don't have non-metricity. So we assume that first of all, teleparallel means that we assume manifold which is flat. So the curvature is almost zero. It's always zero. It's globally zero. And of course, the covariant derivative is also zero. This is an extra condition. So if we remember the first equation that I put at the beginning, you can split this connection in several pieces. So essentially what we are doing here is to assume that non-metricity is zero, but also we are assuming that the connection is zero. So this the general connection, not the Levi-Civita one. This is very important. This is the Levi-Civita connection. Then it should be here a small circle, sorry, but this is the Levi-Civita. So the general connection is equal to zero in this case. And the biseparate connection and the curvature. So if you assume that the curvature is zero, and you make some computations, you end up with a very particular connection that satisfies this condition. This is the so-called Weissenberg connection. The Weissenberg connection is the one that satisfies that you don't have no metricity and the curvature is zero. And it has this very particular form depending on the tetrad and depending on the so-called spin connection. This spin connection needs to be always flat, and also needs to be, in the end, it's just pure gauge in teleparallel gravity. And doing this, you really find that if this spin connection is pure gauge, you notice that the curvature is just identically zero. And this is the condition for teleparallel gravity. Yeah, it's always possible to find a frame such that this spin connection vanish, and this is just a gauge choice. But one needs to be very careful with this choice. I will talk about this later when we are talking about spherical symmetry. So the field strength of our theory in teleparallel gravity is torsion tensor. So we only have torsion. We don't have any other ingredient. Torsion is the responsible of gravity. And in this case, we have the antisymmetric part of the connection in this case, which is the Weissenberg connection. And this is the structure of the torsion tensor in teleparallel gravity. Okay, it's the antisymmetric part of our connection, which is the Weissenberg connection. And this torsion tensor actually in general is not non-vanishing because we have some gravity, so gravity is related to torsion only, and transforms covariantly under both Diffie and also under local Lorentz transformation. This is very important. Very important to say. It transforms under a simultaneous transformation, transformation in the tetrad and in the spin connection. If you only transform the tetrad and you don't transform the spin connection, this tensor has local Lorentz invariance. So you need to really take both the tetrad and the spin connection and perform a local Lorentz transformation of both simultaneously, and then you notice the torsion tensor is actually invariant on the local Lorentz transformation by simultaneous transformation. Okay, so one can by doing some rearrangement of the geometrical. This is just geometry. We haven't introduced gravity so far. If you rearrange the terms again, you can also write down the connection, the general connection as the Levi-Civita part plus the so-called contortion tensor. So this contortion tensor Q is just a combination of torsion tensor. It's a very particular one. And then one can split the curvature in different pieces as well. So if one use this equation in the curvature, and since the curvature is zero, the general curvature is zero, so this general is zero, not this one, the general is zero, and then you just use some algebraic tensor computations, you notice that you have this very nice equation depending only on the contortion tensor. Contortion is this combination. Okay, maybe this is just a little bit technical, but the important thing is that you can write down your geometrical equations by separating torsion terms and separating the Levi-Civita terms. Yeah, and then if you contract this term twice, let's say you have the rich scalar. So this is something very important. If you create the rich scalar, the general one, and then you contract all the other terms appearing in this geometrical equation, you get this very important relationship. So this is a relationship in teleparallel gravity. In teleparallel gravity, the rich scalar is zero, so this is zero. This, and then you can rearrange the term, and you notice that the rich scalar, the standard rich scalar computed from the Levi-Civita connection, is related to two quantities. The first quantity is the so-called torsion scalar. This T, this is a scalar constructed by the free possible contraction of the torsion tensor, but with very particular coefficients here, 1/4, 1/2, and -1. This is the so-called torsion scalar. And then there is also another quantity that we call B, we call a boundary term, because it's like the derivative of the covariant derivative of the vector part of torsion contracted. And this means that the rich scalar differs by this B, which is actually a boundary determinant action with respect to T. These are one of the most important results in teleparallel gravity, because this means that you can formulate a theory which is equivalent to general relativity. I will show this now. So this is the following action. So if you start with this action with minus t in the action, so you start from the principle of teleparallel gravity, you don't have curvature, you only have torsion, and you construct your Lagrangian with just minus t in the action. This is the teleparallel equation of general relativity action. And since I showed you before that t and the Ricci scalar differ just by this boundary term, this means that this theory, the teleparallel, it will give exactly the same equations as general relativity. So if you make the variations now with respect to the theta, because the theta is the dynamical field here, you realize that this action only differs by a boundary term with respect to the Einstein-Hilbert action, and therefore the fields equation are exactly the same as the Einstein fields equation. So this theory is totally equivalent to GR from the point of view of a fields equation. The same prediction as GR, the same exactly all the observations are exactly the same. But now torsion is the responsible of gravity, not curvature. But the prediction are exactly the same. Okay, this is just the standard point of teleparallel equivalent of general relativity. That's how people call it. And then, of course, if we have the teleparallel equation of GR, of course we know that if we are studying black hole, for example, when studying spherical symmetry, we know that this theory only will have Churchill because we only is the same equations as Einstein and Hilbert action. So we only have the Churchill solution as the solution of this theory. But in this talk, I am going to present not the teleparallel equation of GR because this is a little bit boring. I mean, it's just general relativity. The interpretation of gravity is different, but let's say exactly the same as GR. But I am going to present here a modified version of teleparallel gravity. So instead of having this t in the action, which is just GR, you modify this action. And there are different ways how to modify this action from teleparallel gravity. I'm going to present, for the first one, I'm going to present some as a particular theory, which is very interesting. It's like, of course, it's a toy model. Then you need to find the form of f. But if you upgrade this t to any function f of t, and also can be also the function b, the boundary term, then you can construct a modified theory of gravity from teleparallel gravity, which is so-called f of tv gravity. And this theory, for example, contains f of r. So in this particular theory, if you have a particular function, which is this particular combination here, you obtain f of r, for example, in the context of teleparallel equivalent of GR, of teleparallel gravity. And also one can get a very famous theory which is called f of t gravity. F of t gravity is just by upgrading the torsion scalar to any Lagrangian which is depending on t. You can put t squared or t to the power of 3 or whatever. And yeah, there is a lot of literature about these theories, and what I'm going to present is something that is not so much studied in the literature of teleparallel gravity, but is related to how to construct black hole solutions or spherically symmetric solutions in these theories, which is I think is a little bit more complicated than in the standard case of f of r or in the standard case of Riemannian case. There are many subtleties that one needs to be very careful. Okay, the first important subtlety that one has in these theories, like in this f of tv, although it's just FFTV, but you can also do it in more general theories on the field that you like. I mean, just a way to show how this works, how this procedure that you need to use. So in this teleparallel gravity, you have tetrad and you have the spin connection. The spin connection is a flat spin connection and it's pure gauge. Okay, so this means that if you take the variation with respect to the tetrad, you have a set of fields equation. If you take the variation with respect to the flat spin connection, you have another set of fields equation. However, this second, the variation with respect to the spin connection is identically the same as the antisymmetric part of the variation of the tetrad. So this means that it's just enough if you have any action in modified teleparallel gravity, if you just do the variation with respect to the tetrad, and the antisymmetric part of this variation will correspond exactly to the variation of the spin connection. And this means that in this modified teleparallel gravity, we not only have symmetric fields equation, but we also have antisymmetric fields equation. So the first strategy to solve the equation in general, when you have certain symmetries, I don't know, axial symmetry, spherical symmetry, or whatever, is that you go first to the antisymmetric fields equation because they are usually much simpler. You solve the antisymmetric fields equation and then you start solving what happened in the remaining symmetric fields equation. And for this particular f of tv gravity, the equation looks like this. It's a little bit, it looks nice, but it's not so simple. And the thing is that We also have some, in spherical symmetry, we have three equations of motion as well. But not all of them, or not all of these equations are actually independent, because we also have the Bianchi identity. We have the Bianchi identity here, which really means that we have some covariantized conservation of the Einstein tensor. And this in teleparallel gravity is possible to show that if also in f of t gravity, if the antisymmetric part of this equation is satisfied, then we really have that the covariant divergence of equation of motion also vanish, and we have the Bianchi identity. Okay, the Dynamic identities are very useful in this sense to really to find these properties and to find solutions in spherical symmetry. Okay, so now let's go to the symmetry. So we have a spherical symmetry now. We're interested on finding black hole solutions in a spherical symmetry. So I told you before that in teleparallel gravity you have tetrad and the spin connection. The spin connection is pure gauge, and if you write down the Killing equations, you assume certain symmetries, right? So if you do all the computation, you notice that in the end you have these two equations if you want to impose certain symmetries for your space-time. And in the particular Weissenburg gauge, I also told you that it's always possible to go to a specific gauge such that the spin connection vanishes. This is the so-called Weissenburg gauge. It has been proved that the most general spherically symmetric tetrad satisfying spherical symmetry, which means that the connection is spherically symmetric, and also the metric is spherically symmetric, is this one. So this is the most general tetrad that you can find. Remember that the metric has 10 components, but the tetrad has 16 components. So there are 6 extra degrees of freedom that can appear in the tetrad that are related only to Lorentz degrees of freedom. That's why here you can notice the tetrad, you have much more freedom, much more independent functions than in the metric. So you can take this tetrad and you can, for example, you can take the first equation that I put in some slides before, and you can obtain the metric tensor, and this metric will contain only some of the functions appearing here, because other functions will be only related to this Lorentz degrees of freedom. And yeah, in general, this function can depend on the radial coordinate on time. Of course, we are only considering here a static case, no time evolution. Yeah, okay, so if you put this tetrad, the tetrad in the first equation of this f of tv gravity, and this can be even done for a more general field as well, you notice that the antisymmetric fields equation can be solved. And this is what we did with Christian as well some months ago, and it's possible to find that there are only two tetrads that satisfies that can solve the antisymmetric fields equation. The first one is like kind of a real tetrad. This is a real tetrad that has been used in several times in other papers, but also there is another tetrad that was not found before, and it's a complex tetrad. This complex tetrad, if you have this complex tetrad, also you satisfy the antisymmetric fields equation, and the metric is still the same spherically symmetric metric. So this metric is not changing the signature at all. It's just the same metric, but with a complex tetrad. Okay, and of course the phenomenology of these two thetas are different. This is the point. So you have in teleparallel gravity symmetric and antisymmetric fields equation. In the antisymmetric fields equation, you have two possible branches of tetrad solutions, and then you go to two different branches and you study them independently because they have different symmetric fields equation. So they will have different phenomenology. And this is something that we study in this paper. So the first thing is that, okay, I already told you that the first tetrad is well known, and the funny thing about this tetrad is that when you have this parameter chi that appears there that doesn't appear in the metric, it can be plus or minus one. When you choose the minus sign in this tetrad, the torsion scalar behave very in a strange way in the Minkowski limits. So you really need to take like a of r and b of r, the metric functions, going to minus one, which is possible to do here because the metric is a square here. If you notice, all is a square. So you can take the Minkowski limit in a like weird limit to obtain that the torsion scalar vanishes in the Minkowski limit. On the other hand, for the complex tetrad one always has that the torsion scalar is non-zero, even for the Minkowski case. So if you put a and b equal to 1 or a and b equal to minus 1, the torsion scalar is always non-zero. This is a little bit weird as well. Okay, but for the complex tetas, all the quantities, torsion tensor, scalars, complex, are all the metric are all real. So we don't need to care about that it's a complex tetrad or it has these imaginary terms because we couple matter only with the metric tensor, and these imaginary terms are really non-seen from any way. So yeah, so I don't see any problem of this, although there are some opinions in some other authors that may think that it can have some problems when you do some perturbations, but I think I don't see any problems so far here, at least at the background level.
خود اون چیزی که داره پخش
Okay?
میشه.
So this is the situation. In telepathic gravity, you have these two
دو تا
branches,
اسکیل
anti-symmetric fields
متفاوت
equation,
میزنه.
and then you need to go to the symmetric fields equation. The symmetric fields equation are difficult to solve, of course, as any
واخه اینجوری
modified theory
الان
of
به درد
gravity,
ما میخوره.
but we were, in this paper, we were able to find two exact solutions. Two exact solutions that describe a black hole. Because actually they are the first solutions,
نه
exact
دیگه من
solutions in
اینجوریش
telepathic
کردم.
gravity describing black hole solutions.
این
Because
کادرو
there
دارم
were
میگیرم.
some solutions before, but they are kind of trivial in the sense that they are just with torsion scalars constant or zero, or they are not black hole solutions. They are other configurations. And we found, for example, this nice Reiner-Nostrom solution, which is like Reiner-Nostrom, but the GRR components is not exactly the same as the Reiner-Nostrom. This is a black hole solution with two event horizons. And here we have the Q, this parameter Q, which is related, is similar to a charge, but it's not a charge here. It's a constant that appears from the theory. Although the theory here that you have in order to get this black hole solution is very weird. Let's say it's a little bit strange form of F, so it's a little bit ad hoc. More interestingly, in my point of view, is the solution that we found for this so-called Boring-Feld electromagnetism, Boring-Feld f of t gravity that is inspired from Boring-Feld electromagnetism, which has this particular form. For this particular form of f of t gravity, which is called Boring-Field, and you really note, if you do the expansion, you notice that this is just to have general relativity plus some t square component and so on, if you assume that this quantity is small. So for this particular theory, we're able to find an exact black hole solution, which is like, you can say, it's very, very weird. You have some arctan here, arctan terms, but actually this is a black hole solution. We check that this is a black hole solution, and moreover, we check it's possible to see that it's asymptotically a flat solution for a particular combination of the constant. And moreover, we also check that this is a black hole solution with one horizon, just one horizon, and it's very similar to Schwarzschild in this point of view. But the modification of the event horizon is really related to this lambda. Lambda is the parameter, boarding field parameter. And yeah, and you have like a shift in the event horizon given by this lambda. And we are still investigating about the validity of the solution. Okay, and this is related to black hole solution without a scalar field. Now I'm going to talk about the scalarized solutions in teleparallel gravity. As Ludovic introduced very nicely, I will not do this, of course, because Ludovic did much better than me. There are different ways to study scalar-tensor theories. We have different scalarized black holes. One of them is, for example, to have such a theory when you have the rich scalar coupled with the scalar field in a non-trivial way, for example, and then you have a certain potential. And there are a lot of studies about this particular theory. This is Riemannian. It's just Riemannian. And then there are some no-here theorems related to this theory by some particular combination of or some particular choices. But one can actually circumvent the no-here theorems for some particular couplings, this coupling f of phi, and also for some particular potential. So people have found some solutions in this Riemannian case, and they say that there are some scalarized solutions. Also related to Gauss-Bonnet, but okay, this is not related to this. But what I'm going to tell you is that, as Ludovic mentioned, in the Riemannian case, there are many studies about scalarized black hole solutions. Now I'm going to present a similar approach, but in the teleparallel point of view. So to do this, we consider this Lagrangian. So instead of having here the coupling with respect to the rich scalar, now we are coupling the scalar field with the torsion scalar, and we are also coupling, having another coupling with respect to the boundary term. And this part is just the standard part related to the kinetic term and the potential. So this particular theory actually contains the Riemannian case as well. So if you choose this A of phi equal to minus C prime, C tilde, sorry, you automatically, since T and B are related to the rich scalar, automatically you can also get the Riemannian case. So you can think that this teleparallel theory contains the Riemannian case that I showed you before, but also contains other theories that are not possible to obtain in the Riemannian case. So that, for example, you only have torsion scalar couplings, or you only have B coupling, etc. And this is something that we study. So we study what happened with couplings when you only have couplings with T, for example, or you only have couplings with B, plus some general relativity there. Okay? Okay, so the first equation of the theory can be written in this way. So you can write down, or you can put it in a way such that you have general relativity. So this term here, just general relativity, and then the rest, and all the rest will be related to the scalar field. So this is related to the energy momentum tensor of the scalar field. Of course, the first equation looks similar to the Riemannian case, but they are not, of course, the same. They are more general. They contain this other Riemannian case. Yeah, okay, for this paper we use this non-trivial, let's say, representation of the metric, because I think it's much simpler for this case, just a technical detail, it's not so important. And the point is that you can, in this case, I think Ludovic also explained a little bit about this, so the scalar field can have a certain energy, and this energy in the black hole exterior region, and can be defined in this way. This can be important to understand if the solution that we can get are physical or not. This is more or less the idea. Okay, so we have the fields equation. Again, this in teleparallel they have symmetric and antisymmetric fields equation, but we know that antisymmetric fields equation are solved by these two tetrads only, this in complex and the real tetrad, and we will have them two different set of symmetric fields equation again, the one for the complex and the one for the real tetrad. Okay, now for this particular theory, when we have just a coupling with the boundary term plus a GR term, we only found solutions, but they don't look so interesting. I mean, we found some solutions, but I am not going to present them here because they are not so interesting. For the real tetrad. For the real tetrad, again, it seems that the real tetrad is always more complicated. That's the point in this teleparallel gravity. And for the complex tetrad, we were able to find these Churchill-de Sitter solutions with some coupling. So, yeah, this is another solution. Sorry, we found a Churchill-de Sitter solution with certain coupling and certain potential. You can check all the details in the paper, but only for the complex tetrad. It's an exact solution. It's not a numerical. It's an exact solution. And we also found some non-asymptotically flat solutions, which are displayed here, by having non-trivial couplings and having a non-trivial profile for the scalar field. So they are really scalarized solutions. Are they really important? Are they really black hole solutions? This is something that one needs to study further. Are they really non-asymptotically flat? In this case, it's non-asymptotically flat. Okay, but maybe that's why it's not so interesting, the solution. But for the coupling, when you have only coupling with the torsion scalar like this, something like this, we were able to find the exact solution for both, for the real and also for the complex tetrad. And for the real tetrad, we were able to find this solution here, which is similar to having like a Reiner-Nostrom, but with the streamal Reiner-Nostrom case. So you have that the mass is equal to the charge, some kind of relationship with the charge. And in this case, the scalar field has a non-trivial profile in this particular phi square coupling theory, in this particular case. What is interesting for me is that this solution is actually known, but not in teleparallel gravity. It's known in the Riemannian case. There is a particular theory which is called the Riemannian conformal scalar vacuum theory, and this particular theory, which is conformal invariant, this solution is a so-called Bokarova-Bronikov-Melnikov-Bekenstein solution. It's a very old solution from the 80s, I think. But this solution in the Riemannian case is unstable. But in our case, in teleparallel gravity, we don't know if this solution is stable or not because we have different fields equation. So to understand if this solution is stable or not, we will need to really perform some perturbations around this solution. But it's interesting to notice that also in this teleparallel gravity, we also find this kind of black hole solution that it was found before in other contexts, in other theories. Okay. Another interesting scalarized solution that we found is related to this particular coupling. Again, it's phi square, and this particular solution is asymptotically flat. Maybe it's not simple to see here, but it is asymptotically flat, and it contains just one parameter, this k, and also important thing, this is a square. This square is very important in the metric, and if you to understand just the behavior of this scalarized solution, it's an exact solution. It's not numeric. There's no perturbation whatsoever here. It's totally exact. If you assume certain condition for this K, then you can realize that this solution also behaves like Schwarzschild, like some kind of Schwarzschild plus some correctors. And but if you just have the full metric, then it's a black hole solution. But then you need to understand better what is going on with this metric. If it's really an interesting solution or not, we need to study from the phenomenology point of view. But it's always very difficult, as Ludovic also mentioned, to find exact solutions, exact scalarized solutions in the Riemannian case. In our case, in this in teleparallel gravity, in modified teleparallel gravity, we were really able to find exact scalarized solutions, which is I think quite interesting, because in the Riemannian case, as Ludovic mentioned, they only found like numerical results, and also they found this like trivial Schwarzschild solution with a non-dynamical scalar field. In this case, really the scalar field is dynamical, and also is totally non. I didn't put here the form, but is non trivial at all. And then you really have some scalarized black hole solutions. So exact. This is which is very interesting. Okay, and also I don't want to disturb you with more solutions and more equations, but we also you can take a look at the paper if you're interested. But we find also other solutions. Now we need to where when some parameters are control the scalar field. And yeah, for this particular solution, for example, we got in the particular limit when this parameter is small, we got these logarithm terms. These logarithm terms are actually something that always appear in the literature, in the teleparallel literature, when you are expanding around Schwarzschild. So some perturbed solutions, not exact solutions. So it seems that in all of these solutions that people have found in the past, only perturbedly, there should be a more general solution similar to these power law things that you get in the context of other modified theories of gravity. So yeah, this is more or less the idea. Okay, also in our paper with Christian and Ludovic, we formulate some no-here theorems. So we formulated some, there are many technical details, but the thing is that there exists no spherically symmetric, asymptotically flat, scalarized black hole solutions for some specific couplings and some specific potentials. And this is the result. It means just technical things, but you can take a look in the paper. So if you have these four conditions, we are not able to find asymptotically flat scalarized black hole solutions. So actually all the scalarized solutions that we found, that I presented here, they are not part of these four cases, of course, because this is a theorem, of course. These four conditions, if you have any of these four conditions, you don't have black hole solutions, asymptotically flat black hole solutions, scalarized black hole solutions. Okay, so this is more or less what I wanted to present you. So now teleparallel gravity or modified teleparallel gravity can open a different way to understand gravity. Now instead of curvature, now you can use just torsion. You have just torsion in your theory. You can formulate a theory which is equivalent to GR, exactly the same as GR in that point of view of all the interpretation, and there are certain subtleties in the theory, but the fields equation are exactly the same as GR. And then you can modify this theory. So the modification of teleparallel gravity usually is very different to the modification of GR, but the modification of teleparallel gravity, is it always possible to find the equivalence theory of modified Riemannian case in the teleparallel case. So for example, I presented here the f of TV gravity. F of TV gravity has much more possible theory, let's say, in the teleparallel, but you can have f of r, for example. F of r is also there, it's part of the theory. And the same for when you have a scalar field. When you have a scalar field, you can have coupled with the torsion scalar, with the boundary term, but also you can have the standard non-minimally coupled case of the Riemannian case. So you can think that in teleparallel gravity is more general in that point of view. You have more freedom to have more couplings and more terms, but you can always construct theories to have the limit of Riemannian case. And we found the first non-trivial black hole solutions in modified teleparallel gravity in both f of TV gravity, in this particular boring field, for example, which looks interesting, and also we found some exact scalarized black hole solutions. So what is next is really to analyze the stability of them and to really to understand the phenomenology of them. And also, in my opinion, it will be interesting to analyze if it's possible to have some spontaneous scalarization, like in the Gauss-Monnet case that Ludovic was showing, and to really to find if it is possible to find an exact solution for this case, because as Ludovic mentioned, we don't have an exact solution for this. It's just trivial, let's say, it's just structure, but it will be very nice to see if in this teleparallel gravity in this theory, or in a Gauss-Bonnet teleparallel theory of gravity, it's possible to really to obtain an exact scalarized solution with this spontaneous scalarization instead of just having numerics with an exact form, I would say. I think it would be possible, but yeah, we need to see. So yeah, so this is all from my side. So thank you very much. So if you have any question, please let me know.
Okay, thank you, Sebastian, very much for this nice talk. So, are there any questions? Let me see. Yes, Haidar, you can ask. You are muted.
Yeah,
Now.
yeah. Hi, Sebastian. Nice to see you.
Hi.
Thank you so much
Hi.
for your nice talk. Sebastian, my question is about the Lorentz symmetry in teleparallel gravity version for the black holes. So we know usually it will not be conserved satisfactorily. So are these solutions physical or only toy models? Thank you so much.
Yeah, okay, so first of all, Manos, who is here, he has a paper about the covariant version of f of t gravity, okay? So he with Martin Cruchard, they were able to formulate modified teleparallel theories of gravity having Lorentz, being Lorentz invariant. And the point of this is that there is a long discussion about this in the literature. The point is that maybe I can go back to the beginning to show you. In the standard case, when you just have the t in the action, you just have gr, and then your theory is pseudo local invariance. I mean, normally. But then, okay, maybe I can show. Wait a little bit. Yeah. Maybe I click too many times. Yeah. Okay. Yes. Yeah. And the point is the following. So, I can go to the equation here. Here. Oops. Yeah, here. So, okay. So the torsion tensor in general, actually has this form when you have the derivative of the tetrad, but also you have this spin connection here. What happened that in the standard, the first formulation of f of t gravity, people put this spin connection here, these two terms equal to 0, always, always. And if you do this, you notice that the torsion tensor doesn't depend locally on the local Lorentz transformation. But if you take this full form of the torsion tensor, which is the correct form of the torsion tensor, and you simultaneously transform the tetrad and the spin connection under a local Lorentz transformation, you realize that the torsion tensor is invariant on the local Lorentz transformation. So this means that any theory that you can construct from the torsion tensor, f of t, f of tv, or whatever, can be written as a local Lorentz invariance theory by a simultaneous transformation in both the tetrad and the spin connection. And yes, so this means that all what I presented here is compatible with this. So it's compatible with the covariant formulation of f of t gravity or of modified teleparallel gravity. And yeah, and if the solutions are physical or not, this depends on the phenomenology, of course. One is to, for example, for this boring field, this arctan solution that I show you, and now we're investigating what happens with this solution with perihelion shift or shadow or accretion disk. So we need to do some observational analysis to see if these solutions are interesting or not. But from the point of view of the theory, it's kind of understand now that the theory is it's covariant on the local Lorentz transformation under both simultaneous transformation.
Yeah. Thank you.
So,
Thank you. And if possible, I have another maybe stupid question. It's just for my curiosity. We know, for example, the astronomical black holes, and we can imagine, we can explain using the, for example, Riemannian curvature. And if we want to explain them and imagine them using the interparallel gravity and torsion, how we can imagine them? For example, if we want to explain an astronomical version of torsion-based black holes, how we
yeah.
can imagine them?
Yeah, in the end here, I mean here, we only couple matter with the metric. So what we really see in observations is really the metric in it. So for example, if you have, imagine that all of these, for example, this solution here. Okay, this solution here, you have the metric here. This is the form of the metric, which is not Schwarzschild, but in a particular limit, is when lambda, for example, is very big, this means that this is very similar to Schwarzschild. So this solution, for example, you just have the metric and then you can analyze phenomenology, for example. You can analyze the shadow of the black hole. In teleparallel gravity, you have the geodesic equation as well. In this version of teleparallel gravity, because we only couple matter with the metric.
I know, but in real physical sense, in our space-time, we can imagine the curvature, okay? And we see observationally, for example, sun, other planets, or etc., and we can explain them based on the Einstein version of gravity. But if we want to imagine them, and if we want to interpret them based on torsion gravity, how we can, because in torsion gravity usually we neglect the curvature, yes, and so how we can I know this formulation is parallel to the Einstein version of gravity, we know, but if we want to make sense how we can imagine them, how we can explain them in real physics, not in mathematics.
Yeah, in real physics, is the teleparallel current is exactly the same as GR. You have the sun, you have the planets, and the planets are orbiting the sun in the geodesic motion. And you have exactly the same prediction as general relativity. It's just that now the responsible of this is torsion tensor, and the geodesic equation is exactly the same as GR, but the geodesic equation is very similar. If you translate all into the teleparallel language, it's more similar to a force. So it's really it's like acting similarly as a force, but the mathematical structure of the geodesic equation is the same as the geodesic equation. So you can think more is this f of t or teleparallel gravity more as the old ways of understanding gravity, more related to the force, but the prediction are exactly the same. So in the physical real world, there is no way to distinguish between the teleparallel current of GR or GR. It's exactly the same prediction.
Yeah,
So there is no way to distinguish. But then if you modify these theories, of course you have different prediction. Depending how you modify the theory. But yeah, this is more or less the answer that I can give.
Yeah, thank you so much. Thank you, Sebastian. Thank you so much.
Yeah, welcome.
Okay, so I think we have to stop here. So thank you, Sebastian, very much for your talk and the discussion.